Hello everyone and welcome to the solutions video for Codeforces Round 772. Now I know I didn't make any solutions video for the last 2 weeks. The reason was for the first week I was working on reconstructing A20J and the contest went bad, and the second week also the contest just went bad. So I didn't have anything to make solutions for. And today it almost went good, so I'll be explaining A to D. Even though I FST'd B, I know the solution, so we're going to be discussing that. And with that being said, let's begin after making sure you have subscribed. Okay, that was pretty terrible. So problem A, min or sum. In this problem, we are given an array with n elements, and what we want to do is minimize the sum of its elements. So we want to minimize this value, and what operation we can do is we can pick two elements ai and aj and change them to x and y such that x or y remains equals to ai or aj. So this is the invariant, that the or of the elements that are being operated on does not change. Now what does that mean? That means that if any bit is set in any number, it cannot really get unset because its OR taken with any other number will have that bit. For example, if we take 4 and let's say 3, so that's 3, their OR, let's take 2, okay. So their OR is this value. And as you can see, since this bit was set in 6, this will remain fixed, and since this was also fixed in either of them remains there, and this which is not fixed, and by fixed I mean 1, which is not on in any of them, it is 0. So after that operation the bits do not really change. So let's see how we can transform it. Since we want to minimize sum, it would be best if we make one of them 0 and the other one the OR of them. The reason being, we are able to omit some of the bits because this bit was common with this. I was able to omit this, and so this won't be able to contribute to the sum. Since every bit must occur once, if I just condense all these bits into one number, and let's say that is a1, that would become a1 or a2 or a3 up to or an. So this number will contain all the bits and all other numbers will become 0. So this will maximize the sum while satisfying the constraint, because all the bits that were on in any of the number are still remaining on, and the sum is minimum because I am omitting as many bits as I can. That is every duplicate occurrence of any bit. So the final array would look like this: a1, which is this, and all other values 0. So the sum would be just this value, the OR of every value. And that is what I have done here. Take input and calculate the OR of every element. Okay, so problem B. Now I have FST'd this, but that is due to a silly reason. We are not going to mention that. Actually, it is because of Copilot. So I made a typo, and that typo happened because I thought that Copilot's autocomplete would be good. It wasn't. So let's see what this problem is. So we have a problem here that a1, a2, a3. We have an array, and what we want to do is we want that none of its elements should be a local maxima. That is, so an element ai is a local maxima if ai minus 1 and ai plus 1 both are less than it. What we want to do is we want to remove all the local maximas, and how we can do that is pick any element and change it to anything else. So that is the operation. So how do we do this? Well, let's have a look at one of the maximas I mean. So this maxima, how can you remove this maxima? Well, if you make this 3 As you can see, this is no longer a maxima because we want greater than, strictly greater than. So in one operation, I can remove one maxima. So an upper bound on number of elements for now is number of local maxima. On number of operations is number of local maximas. Can I improve upon it? Well, take this situation where there is a maxima, so like 5, then there is a minima, and then there is another maxima. So it is like up, down, up, down. And now one thing I can do is make this 3 and make this 2, and then this would be 3, 3, 1, 2, 2. No local maxima, is only a local minima. But this takes 2 operations. However, what I can do is, so it was like this. I can make 1 to be 5, and then what will happen is, erase this, and then since this is 5, so it becomes like this, and so I will be able to remove local maximas. So that is pretty much the only case where we want to consider something else, because in all other cases changing something else doesn't really work. So one thing you can do is find out all the maximas and then see which of them occur like this. So like instantly, there's no other number either in between them. So capital M is maxima and small m is minima. So when they occur simultaneously, then I can choose this. Otherwise, I just choose this. And this is what I did. So let me show you. So as you can see, I took input and then I stored in V all the local maximas, and then I iterated through them, and whenever 2 local maximas had a local minima in between them, in that case what I did is so obviously 2 local maximas will have a minima in between them, so that is why I'm just checking the distance between them is 2, and then I push into W. W is the final elements that I'm going to be changing, and then for every element in W I'm checking which one is the biggest one among its adjacent elements, and I change it to that. So this is one way to approach it. The another is that, okay, so let's go back to the part where we knew that, let's say it is, the elements are like this. So there is a local maxima here, 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 and here. So the number of operations are at maximum 4. So 1, 2, 3, 4. And on changing that maxima, I'm able to remove that maxima. But what if I change, so if it is I change I plus 1. If it was like 5, 1, 1, 5, 2, if I change this to 5, the maxima is destroyed, right? But what this also does for us is it is able to contribute to destroying the maxima which can be here. So let's say it was like 1, 5, 2, 4. If I make 2 to be 5, then I'm able to destroy another maxima, right? So because it is to the right of it, it is able to not just destroy this maxima, but also contribute to the other ones. So with that greedy approach, we can just try to change all the elements one after all the maximas, and what we change it to, its biggest neighbor. Because let's take this example, 1, 5, 2, 7. So we have to change it to 7 and not 2 and not 5, and then it will be able to destroy 2 maximas at once. So that is another solution that would be more neat and clean, but both work. Main thing is you had to understand this edge case of simultaneously occurring maxima, minima, maxima without any element in between. Okay, let's look at problem C now. Problem C, differential sorting. So in this problem, we again have an array just like always, and we want to sort this. Basically, not exactly sort, we want to make it increasing sequence, so it can be like 1 1 2 3 4 4 5, not strictly increasing, just increasing. So let's see what we can do that. What we are allowed to do is pick three numbers x, y, z, x less than y less than z, and this is important. Okay, this is important. So pick three numbers x less than y less than z, x, y, z, and what we do is we change ax to ay minus az. So notice that if I want to change xth element, I need at least two elements after it. Otherwise, I won't be able to change it. That means that the last element, an, remains the same, and so does an minus 1. Only an minus 2, an minus 3, and a1 are able to change. So let's see if we want to change them and how we want to change them. And also, we are allowed to do at most n operations. We don't have to minimize the number of operations, we just have to make it into a increasing array. So let's try to visualize this. So this is an, okay, so this is an. Now if an minus 1 is bigger than an, we will never get a increasing sequence because I cannot change it. So in that case, obviously say that it's not possible. However, let's say it is smaller than this. In that case, this is an minus 1, right? So, and now let's look at the next element. Now, whatever it is, okay, I don't care. You see, an minus 1 minus an will always be a negative number. Because it is a negative number, it will always be smaller than these. I'm considering both of them are positive, right? Okay. So since it will always be smaller, what I can do is for n minus 2 to up to a1, I apply operation with one of them being I, whichever index I'm processing, n minus 1 and n. And so let's say this was x, so I will get minus x over here. And then for the other ones as well, I can just make them minus x because this is also increasing, right? So that's cool. Now let's see what happens when this is actually negative. Okay, so when both were positive, it worked pretty well. Now let's consider an minus 1 to be negative. If this is negative, the equation remains pretty much the same. An minus 1 minus an would still give us a negative number, which will be smaller than an minus 1. So we can just do the same thing again. However, what if an was also negative? So if an was also negative, obviously an minus 1 will have to be more negative than it. But notice now that an minus 2, so notice now that no matter what operation I do, okay, this is only 1 for now, this value x, this first of all will be, so let's say it was like minus 5, this was minus 2, we'll get like minus 3. So that value will always be less than an minus 1. So because it will be less than it in terms of negative, so hence it would be more than it, so it would be something like this, and so we won't get strictly increasing. So in that case, I'm gonna have to rely on an minus 2 being smaller than this, and an minus 3, and so on. And basically, why, like, there are more operations here, you might be thinking that, yeah, so why can't these help? Well, they will also make everything bigger, something like this. So minus x, minus y, minus z, they are all bigger than these elements and smaller in terms of negative. So that is why we cannot do that operation, and I'm gonna have to rely on them on already being sorted. So that is like, you can consider it as a simple edge case, and hence if it is already sorted, then you return, yeah, no operations required. If it is not, then I'm gonna want an to be greater than an minus 1, and an minus 1 can be anything, I don't care. So whatever this x value is, I will then just perform that operation on n minus 2 to 1 and will get that answer, right? So that is what I can do, and what I have done here is slightly different, but it's pretty same. So I have jk and I, so jk would represent, so I was thinking that j and k may be different, but they don't really need to be different because I had read the problem wrong. So I'm iterating from the right side and I'm checking if the current one is bigger than the next one, then I break out and say it's not possible. Otherwise I check. Okay, so this is basically happening at only n minus 2, and I'm just checking that ai is smaller than ai plus 1, and so that would give me a value which is less than ai, and in that case I'll just say j is n plus 1, n minus 1, and k is n, and then I break out of this, and then I iterate from n minus 2 and or n minus 3 because it is 0 based to 0, and then I just perform the operation because I don't have to minimize the operations, and this loop take cares of this edge case of all negatives in sorted order because this will never happen to be false. So this was a weird way to do it because I had read the problem wrong, so I was solving something else and then I transformed it into it. So that was problem C. Now let's look at problem D. Okay, so this was a good problem. We're given an array once again and everything is unique. Now what we do is we generate a set S, and what this contains is first of all the elements of array, and then also for every element in this set, so this set is infinite, for every element in this set we create a new element like this. So let's say I had some element x in this set, then I add 2x plus 1 and 4x into this set, and so I get two new elements, and so the set can go on up to infinity. Now we are given some value p, which is pretty big, 2e5, and we want to tell how many elements in this, how many unique elements, because it is a set, so how many unique elements will be present in this set such that they are less than 2 to the power p. Now this is where it gets dangerous. 2 to the power p. How do we do that? Well, here you have to analyze this operation. Now you might be thinking this is pretty simple, but obviously that's where we have to start. So let's look at this operation. Okay. So this operation, so let's take, yeah, what is this? Yeah. So let's take some element like this. So it's the binary representation of x. Now notice that 2x plus 1, what it does is it creates a number 1 1 0 0 1 0 0, the same number, and adds a 1 to its right. And this, so this is the same 0 0, this is the same part, and adds two zeros. That's what multiplying by 4 is, and this is what adding multiplying by 2 and adding 1 is. So what does this tell us? This tells us that every operation creates a new element with a different MSB, most significant bit. So and so since everyone is creating two, that means if we were to count how many elements are there with some particular MSB, then that, so let's say for MSB equals to I, the number of elements that I will get would be something like, so let's call this f. So f of I would be equals to f of I minus 1, right? These will, so let's call this operation 1 and operation 2. So this will be formed by operation 1 and this will be formed by operation 2. So as you can see, there is some overlapping sub problems and stuff, and so we can form a DP. And if you were not able to think that maybe we might have needed DP, let me tell you, when you are not able to think that combinatorics, some counting problem is not being able to solve by normally counting by greedy methods or something like combinatorics like NCR and factorials, then you should resort to DP. And here, let's look at our DP again. So our DP I is the number of unique elements in that set where MSB is I. So if so, DP2 can be something like can have these elements, right? And so its count would be 3. So if we have DPI, then DP, so if you want to calculate DPI, then it is just DPI minus 1 plus DPI minus 2. First of all, let's see if there is any overlap between elements in this and this, because we only want to count the unique ones. Well, there won't be any. Why? Because every unique element in this will create one unique element only, right? Because we are only applying the operation 1. And every unique element in this will create only one unique element because we are applying operation 2. But what is the guarantee that there won't be any overlap among them? And the guarantee is that this always creates an odd number and this always creates an even number, because this is 2x plus 1 and this is 4x. I mean, the operation 1 is and operation 2 is 4x. So that is why these will never overlap. So DPI is just this much. Cool. And then what we can do is count how many numbers in the original array also had MSB I, and we can also add them. So let's call them count. So count I in the array A, right? Is that enough? No, it is not. Why? Let's take this example. So 1, and the elements have, the array elements are 1 and 4. So DP0 is really nothing. So DP1, wait, is DP0 something? I don't know. So DP0 is 1, right? Because it has one element with 0th bit as MSB. Then 1, how many will I get in 1? From 1, if I multiply it by 2 and add 1. Okay, sorry, this does not even count in 0. This count at 1 first MSB, right? So DP0 is 0 and DP1 is 1. Then DP2, what is DP2? DP2 is so perform the first operation, we get 3. So that, and that's the only number with MSB as 2. So we get 1 again here. And then when we are counting this, the one with MSB 3, so 1, 2, 4, right? So we will add these two, right? So I'll have 2 and then I'll add 1 more because this 4 exists. However, this 4 should not be there because this 4 will come from this only, because this, when transforms, becomes 4 only, right? So that means I shouldn't have added 4 here from this. So how do I avoid this? One simple way is to just see which elements will I eventually get back in the array. So if my array had 1, 2, 4 and 6, sorry, and 5, 4 will eventually come from 1. So I can just remove 4 from array, and 2 and 5 will eventually come from 2. So I can remove 5 as well. If I had 3, I could remove 3 as well. So remove the elements which I will eventually get, and then apply this DP. Pretty simple. Now here, the wrong answer you're seeing is because of me depending once again on Copilot's code. I mean, it was like half a line of autocomplete. I thought it is correct. And so here's the problem with a Copilot. It generates some code suggestion. So now I have to process that and check if it is correct. And that is way more buggy or bug prone than writing the code myself. So that is why I have now just disabled Copilot. It wasn't a good choice. So let's see what this is. So here I have NP A. I created a set of all the elements because I want to know all the elements there are in that. And then V represents the final form of A, that is after removing all the eventually. So basically removing elements like this. I did not have a good word for that. So for every element X, what I'm doing, so I'm copying it in K. I could have just removed X here, reference here. So if it is an odd number and greater than 1, then it can be formed from something. And if it is even number and greater than equals to 4, sorry, divisible by 4. So based on what kind of number it is, I perform that operation, and obviously this happens in log of AI, log of X basically. And if at any point I encounter this number in my set, I say, okay, this is obtainable, breakout. If it was not obtainable, only then insert it into V. Now I create the DP, and obviously the numbers don't exceed something like 2 to the power 30, but I'm just adding extra because there's no extra time complexity. So I check. So first of all, I need to make sure how many elements are less than the elements that I require. So let's say I'm checking this MSB, right? So I need to check all the elements that are less than MSB this. So I get this less than value, and while v dot size, so basically for null check, and while the first element in V is less than it, I erase it and increase my DP value. And obviously due to this, so let's say it was like 1 2 4 6, so 1 gets consumed during the first iteration, 2 gets consumed in the next, 4 and 6 get consumed in the next. So that's great. And also they are not too much counting. Every element is only added once and removed once. And now after that, dpi equals to dpi minus 1 plus I minus 2. This is just checking to not get out of bounds, and then take the modulo and add to the answer, because dpi only represents the values that the unique values that have MSBI. So I have to count for all MSBs less than P, because we conveniently have to calculate less than 2 to the power P. So that was also another hint that you might need some linear multiplied by something else complexity kind of solution for this, because P is very big. So yeah, and then I just print the answer, the most important part. So that was the solution for A, B, C, and D. Sucks for me because I FSG'd B, but it is what it is. Leave a like and subscribe to relieve my suffering of getting another negative delta even at expert. Anyhow, with that said, bye.